All right, in today's unit, what we want to try to understand is why some sounds have a more rough or disagreeable, or what musicians have long called a more dissonant character than others. And we know, I mean, from our musical training, that if we have an octave or a unison, that we won't necessarily experience this. Or if we have a fifth, that is an interval with a frequency ratio of, let's say, 3 to 2, we're going to not notice as much roughness there. But if we have a very tiny interval, like a minor second or a major second, we'll experience what is called dissonance. And now, what's going to be important to recognize is that what we're going to try to cover in this unit is the sensory origins of this experience of dissonance. And we'll see that it'll tell us a lot about the musical behavior of these combinations of tones, but it's not going to be the whole story. We'll see that if we look at, later on, we'll look at the history of consonance and dissonance, and we'll see that over the years there's been a lot of debate about which intervals are dissonant and which are consonant. In fact, we'll see even today that if you think about it reasonably in a certain way, you'll see that the fourth and the fifth, in fact, are equivalent to each other. But that's not the case in musical practice. People think of the fourth as being a more dissonant interval than fifth. But what we're going to do is set aside a lot of the extra and important, very musically important features of consonant dissonance, and just concentrate on what the auditory periphery is doing, that is the cochlea itself, the kind of information that it's sending up the auditory nerve to the brain about how rough or smooth various combinations of sounds are. Now, the first thing that we want to address is that the ear, and in previous units we've laid out the sort of external structure of the ear. Here we're going to concentrate on what goes on in the cochlea, and in particular what goes on in the basilar membrane. And in a way, we're going to sort of quickly shift to the notion that the output of the basilar membrane, in fact, functions very much like a filter bank. That is a bank of frequency selective elements. And we know that the membrane is laid out in such a way that at the beginning of it we have a high frequency response, and then as this wave travels down, we've seen in an earlier unit, traveling wave, we've seen where that it's the peak of this traveling wave that gives us the frequency information, the place along the basilar membrane where stimulation is maximal. And of course, remind you that on this membrane are, in fact, transducers that transduce mechanical information into neural information. And these units are called the hair cells. And so as the membrane moves, the hair cells bend and stimulate, produce neural firings that are tonotopically mapped. That means that they're dependent on the frequency in the auditory nerve. So you can think of the auditory nerve as a bank of neurons tuned to different frequencies, and they innervate or are connected to these hair cells eventually on the membrane that are located in different positions. So we have a frequency analyzer. The hair cells are frequency selective. So we might ask the question, how selective are they? And now we want to introduce this notion of a filter. Let me just say a few words about a filter. We're going to make our usual plot of frequency versus amplitude. And we can represent a filter like this. In fact, this type of filter is called a band pass filter. That is, it selects only the frequencies that are between its lower and upper bound. And in fact, we talk about the bandwidth of a filter. And of course, there's a very nice mathematical way of defining that. This width is called the bandwidth. And what's really important about a filter is that if two frequency components appear in the filter, and if we're only looking at the output of the filter itself, then we can't hear them out as separate tones. They've just excited the filter itself, and we aren't getting any, let's say, the frequency resolution of this filter is limited by its bandwidth. If the bandwidth is very narrow, then it's going to be very selective, and if we had these filters laid out in this manner, sort of, we could, if we had a frequency exciting this filter and a frequency exciting this filter, then we could say that we have a way of separating those frequencies. But if the two frequencies fall within a particular filter very much and don't activate other filters, then we have a difficult time separating them. So in some sense, the width of these filters tells us something about the frequency selectivity or frequency resolution of the ear. Now, there are many psychoacoustic studies that have addressed the issue of measuring the properties of this filter, its shape, its bandwidth, and so on. And right now, I think after really literally hundreds of research papers and so on, we've got a pretty good idea of the size of these filters, their bandwidth, and the shape, and the properties. And we can build a pretty good simulation of the filter. Now, what we're going to do in this unit is spend some time just playing with a model of the ear that has a filter bank, and then we're going to take various musical materials that you want to play with and pass them through these filter banks and see what's going on in this simulation of the auditory nerve, the information that would be passed on to the brain. And I think we'll see that we get a lot of useful information. And in other units, we're going to see how we can use this filter bank and some post-processing afterwards to get estimates of what the pitch is. We're going to also be able to say things about harmony and timbre and other features of musical stimuli, what the ear is passing on to the brain. And of course, all along, you must always remember that this is a bottom-up view of the system. We're looking at things from the periphery on up to the brain, but there's a very important top-down element. In other words, I don't want to make the system sound too simple here. Turns out hypotheses and the accumulation of experience which we have in analyzing auditory scenes lead us to have an interpretation of this information. And in fact, we know, for example, that the behavior of this membrane is influenced by can be influenced by higher level concepts, and that would be a kind of top-down view. But we're just going to concentrate today on the bottom-up feature. So let's take a look at some examples now where we just play with two pure tones that are at some distance from each other. And in these experiments, what we want to see is to what extent you can hear two separate sounds. You can hear them out as where you can isolate them, hear them analytically, resolve them into two components, and where, as they get close together, when they enter into the same frequency region, we can no longer resolve them, and we begin to hear beats, interactions among the tones. So we're going to spend some time on that, and urge you to play with the interactive tool that we've developed. Now so now what we're going to do is examine, and we want to do this experientially, really, you can get an intuitive grip on it. We're going to have two tones. We'll hold one fixed. We're going to move the other nearer or farther from it. And then we're going to look at at what distance we can begin to hear two separate tones, hear them out as a composite, as two distinct tones versus two interacting tones. And when they're inside of this auditory filter, they're going to interact with each other, they're going to beat, and when they're outside of that region, they're going to be heard as distinct tones. So on the computer graphic that you'll have in your interactive system, we're going to have this fixed tone, and you'll be able to set the frequency of it. Why don't we set it to 440 just for the moment? And then what we're going to be able to do is move the frequency of the moving tone over here, and we're going to keep these as sine waves. So as the and then we're going to look at it. Now it turns out that at a given center frequency, which is where we're going to shoot the width, we're going to show the width of the auditory filter roughly in this manner. So, by the way, I haven't used this term. This, in the literature on psychoacoustics, is called the critical bandwidth. And actually in more modern literature, and particularly out of the laboratories in the United Kingdom at Cambridge, where Roy Patterson is and Brian Moore and so on, they like the term the equal rectangular equivalent, excuse me, I better check on that. Equivalent rectangular bandwidth. And I think we need to refine why that, because I think just aside here, the reason I've drawn the rectangular like bandwidth, it's just, if I drew the other kind of plot here where I had frequency and amplitude, this would be the equivalent rectangular bandwidth to this other really more true estimate of what the filter looked like. And so now we're going to, as this tone glides up through here, now here we're going to have a two-tone experience throughout, and then we're going to get in here and we're going to begin to hear the interaction between this particular tone and frequency. So let's see, let's put the 440 right here. And see, now we got to think about how to do the interface for this, because so now we're going to hear, we're not going to hear this as a separate tone, and then of course on this side of it as well, this is going to keep going up, we're going to hear two tones. But in here we have a kind of one-tone experience. Now, here we're lower, and we're going to ask ourselves, well, first of all, what is the pitch that we hear? Well, the pitch, it turns out, is going to be a kind of average, funny average of these two. And so it's going to move through there. I'm taking this directly from this diagram that was in the Rotor book that I use in class and so on. I've got copies of this and so on. And then we're going to hear beats. It's going to get really rough in this region, right here, where let's say the beats are between 70 hertz and 30 hertz, and of course that's going to depend on the bandwidth here. And so this is going to be roughness, And then it's going to get smooth again when it gets real close, because the beats will be quite slow. So as you play with the position of this tone with respect to the other, of course, you can look at what the frequencies are on these little number boxes on the side. I'm inventing the interface as I go here. You can see that, well, this would be the fixed frequency, and then here's the moving mobile frequency. And so at 447, we see that we've got 7 hertz beats, and this would be the beat frequency, which would be shown here. It would be 7 hertz, because we calculate the beat frequency by looking at the difference between the two tones. Now, beats. What do beats look? What do beats do to the signal itself? What's actually going on? Well, maybe we can look at a graphic representation of the waveform, and maybe look at that in these various regions. Okay. Whoops. What I want to do here is so. What we'll see is that as things beat, they are so here's the waveform. It's being amplitude. This is amplitude modulation. So this part of it here we call amplitude modulation. In other words, the amplitude is going up and down. And in fact, when it's really slow, you might describe this as tremolo. And when it's really fast, you'll hear it as another kind of color or texture on top of the tone, which is rough. Now, so if we look at the spectrum of it, it's always good to think of having, by the way, time domain views and spectral views. So the spectrum here looks like this. We have frequency and amplitude. And here are the two tones. Here's the 440, and here's the 437. And there's a 3 hertz difference, so there we'll see these beats happened at 3 hertz. So now we've really looked at only one tone interacting with another, and we know that in real music and real musical tones, the situation's quite a bit more complicated, because tones have harmonics. If they're harmonic tones or tones coming from sustaining instruments like violins and so on, they may have some of their own amplitude fluctuations because of the way they work, and in fact the musician might be imposing a tremolo on the tones to begin with. So anyway, it's a complicated situation where we have tones sounding simultaneously, and the different components of the tones are falling into different auditory filters, and we're getting roughness from different locations in the spectrum. And what's really important, and we'll see this in another interactive demo that we're going to bring you into in a moment, is that the kind of musical interval, that is, let's look, we're going to examine dyads for a while in the next example, and see how they work. So let me put up the next, and this is the other patch. Now, while I'm working on drawing this thing, you might ask, what is the width? What are the measurements of the width of this equal rectangular bandwidth? What are the estimates of the width of the critical band, of the auditory filter itself? Well, it turns out that above 250 hertz, now 250 hertz, as you know, is about pretty darn close to middle C on the piano. So from there on up, they're about 1/3 of an octave wide. Now that seems like it's pretty wide, doesn't it? Well, we'll try to answer the question is how in the world can we separate or hear intervals or hear out separate tones if they're falling within the same critical band? Well, it's a problem we're going to have to address a little later. Now, in the low register, we're just looking at what we want to concentrate on here is the notion of these amplitude fluctuations, this origin of the sensory experience of dissonance, and we'll leave some of the other questions aside. But when you get down into the lower register, it turns out, and I think I would want to have a diagram here showing how this ERB widens out in the low register. Turns out in the bass frequencies, it can get really quite wide. In fact, when it really gets down in the register near the bottom of the piano, it's almost an octave wide. I gotta look at the measurements more carefully, just so I don't want that to go to press. I got to look at it at the function exactly. It's awfully wide down there, and then it gets narrower and narrower as we get up into the middle register, and then it seems to be a nice uniform third octave roughly from there on up. So now another thing that's very important to remember, you've probably all seen the output of filter banks. They're all over the place in iTunes or on your hi-fi systems and so on. And what's important to recognize about these filter banks of that sort is that they're laid out in this manner, but in the auditory system, this is a continuum. Well, not quite. They're individual hair cells, but this filter bank doesn't work quite this way. They're just, you can think of all sorts of overlapping filters around the various locations on the membrane in a continuum, and there is some overlap among them and so on, and that's going to be important for us. That's a feature of the system that we'll address in a later lecture, but it's not as if it's exactly like your hi-fi, like your audio system at home, where you move along in the low frequency and then you jump into a new filter and then you jump into a new filter. When you sound a tone and then you add a new tone, you can think of it one with respect to the other rather than in this discrete filter bank setup. But this is a good analogy, though, in other respects. It's because the interesting thing is that the audio industry, audio industry, I don't like that term. Audio engineers have discovered that a reasonable arrangement of these things is in fact in third octaves. And so they attempt in their designs to approximate a graphic equalizer of high quality graphic equalizers tend to be third octave filter banks. In some sense, they're addressing the sensitivity or the resolving power of the auditory system in so doing. So that's an interesting connection to make. I hadn't thought of making in this lecture already. So, and there's a whole history there about how that happened. Now, let's move on to what happens with complex tones when they interact with each other. So in the next demo, what we're going to have is the ability to control the spectral content. Now remember, the fundamental frequency in our notation that we're using throughout the course is that F0 is the fundamental frequency. And the harmonics are then 2 times F0, that would be the second harmonic, 3 times F0, and so on. So we'll be able to specify where F0 is and what the amplitudes are for the frequency components in that spectrum. Now, what's interesting is what we're going to do is provide you with 2 So we have another F0 over here, and you can control its spectrum. And so what we'll do is hold one of these fixed, as we did before, and allow you to move this complex signal around. And we'll also supply a way for you to choose different kinds of intervals, like unison, minor second, etc. Okay, fifths, tritones, etc., just like I have in that example. And in addition to that, we're going to allow you to choose the kind of tuning system that people are using here. So we might have equal temperament and just intonation. That'd be, the frequency ratios are really perfect. And then maybe a few others, like mean tone or Werkmeister and so on, or some arbitrary tuning system that you'd like to tinker with. So here we're able to now experience what happens when we have a dyad, a two-tone interval. And what we'll see is that there's and in fact, okay, there's another kind of diagram I'm going to get to in a minute. What we're going to be able to do is play with the idea of how these different intervals sound and how messing with their spectra changes them. And some of the things that we're going to notice is that if we have pure tones, just sine tones, we won't get the beating for the large intervals. But yet, if you've had musical training and you understand, you're going to know that there's sevenths, and you're going to know about these other features that we associate with those intervals, namely that they're dissonant. But if you haven't had that experience, you might think of them as somewhat like octaves or so on that are actually very smooth. By the way, there's a thesis up there, Mary Kay Fida, in which we demonstrate that very, very clearly, that non-musicians tend to think sevenths and octaves are pretty much alike, although they recognize that octaves are wider, but in terms of this smoothness thing, they're smooth, and whereas the trained musicians tend to think of sevenths on sine tones as equivalent to sevenths on complex tones. They're spatial, this is an aside here, the multidimensional scaling experiments show them they have two different kind of structures. One of the rare cases where there are big differences between musicians and non-musicians. Anyway, so now I'd invite you to play with these spectra, play with the intervals, and we're going to provide you also the ability to have various microtonal arrangements where you can move this tone with respect to each other in a continuous way. So there'll be a little menu like there is in the real one where you can actually glide it with respect to other. And then some experiments that are worth trying are playing with odd harmonic spectra, because some musical instruments like the clarinet and the flute, depending on the manner in which it's played, and the register that it's in will, in fact, give rise to just tend to have odd harmonics. And you can hear the effects of these. And so we have a kind of combination here of frequency separation, or tuning, or interval selection, and orchestration going on, where we're playing with the spectral content of these instruments. Now, and what we're going to notice is that there's a hierarchy of intervals, and so what we've prepared for you is another way of experiencing these same kinds of things, and I'm going to draw that up here. So this is going to be the dissonance. I'm going to call this constant. Let's see. I'm not quite ready to say that dissonance is the opposite of consonance and so on. So I'm going to talk about roughness. Roughness decreases. So let's see. That's right. Roughness gets worse as we go down here. So if we have the unison, very smooth, and then we when it's still real close, we're going to have this thing's going to start to get rougher until we get like to a minor second. And then we're going to come around to thirds, right? Major and minor thirds. And then we're going to get to the fourth. It's going to be less dissonant. And then we're going to get to the fifth. And then we've got down again, always going down. We got sixths, okay, and then seventh's going to get. Oh, let's see now. All right, good. Seventh, minor, no, seventh's pretty rough. Anyway, look, there we go. Just go back up for the octave. So here's the unison, and then the octave. Okay. And so maybe one way to manipulate the interface, just so you can experience this with respect to these intervals, is to move your cursor along the bottom here. And so now we're going one tone against the other. You know, maybe we'll have this all linked together so it's all totally interactive. So you're going to see, although you got to be careful because this applies only to a certain tuning system. It's not going to apply to some very weird way of tuning. But the point is that as you go along here, you can hear, you know, the constants getting in, and so on. And that's also going to depend on the thing. So what we'll try to do is arrange this so maybe that we have these estimates coming out of our MATLAB program or whatever showing up here. It's an idea. I mean, that's something we need to talk about. Maybe there'll be, you know, this goes through the ear model, and then we get this, and then you can move about. Well, it's a pretty complicated little piece of software, but it can be very informative. What I did when I was demonstrating this in Earcom, I made these pre-canned. So what I would do is have the one tone go against the other, and I'd stay on that interval, then I'd glide through it, and you'd hear it get rough, and then I'd hang there on that interval, and then hang there on that interval. But then I said, let's do it the other way, so that we go and hang in the roughest locations, just to illustrate the point. So then I picked, we get real smooth, and I get really rough, and I hang there for quite a while, and then I glide through the smoother parts, and then hang where the really roughness. It's kind of like the negative image of this thing. And I always liked the way that sounded. In fact, I was always thinking of trying to do something with those low points, where everything was pretty rough. And there's still a hierarchy there in that, but I never. But I made that back in the in the 70s, in some stuff I'd prepared on in Music 10. It was, yeah, just some where I had it on I had the drawing, and then you actually couldn't manipulate it. It would just go through like this real slowly, and it would just hang there, and it would hang there and hang there. So that might be an interesting thing. And then one of the things I want to do is talk about the relationship between this diagram and tone profiles, because this turns out to be related to also the scale structures and so on. And that's pretty weirdly hard to explain why those two would be coincidentally. But, you know, Krumhansel in the book has, I gotta take this. Cut. Okay, now, what we'd like to do next is, instead of playing with these pure tone or strictly composed spectra and so on, I'd like to start playing with real instrument tones. So what we're going to do is substitute for these real samples of musical instruments that we've obtained from our sample library associated with this site. And so we might plug in a violin and a trumpet, or two violins, or whatever. And what we're also going to do is give you the option of playing these two sounds out of two different loudspeakers, because that's going to be important, because actually in a real musical context with normal instruments, people are located at different locations in space. And what we're going to see by doing that is that the spatial location of the instruments with respect to each other is going to influence the sensation that we have of consonance, or the dissonance, the roughness as well. And if we go to the really extreme case, which we encourage you to do, put some headphones on where you have one instrument coming in one ear, the other instrument coming in the other ear, Now we are going to have some interaction between the two ears because of the fact that sound is transmitted across our head by the bones. It's called bone conduction. So they're not completely isolated, but they're pretty well isolated. And what you'll see in doing that is that this whole idea of beats and so on is going to change somewhat because we don't have real strong, there are binaural beats, but they're nowhere near as strong as when they're coming out of the same speaker location. And this is the Bregman Wright. I'm leading into that kind of stuff too. So I wanted to include that, the idea that these things need to be in stereo. And we want to instruct people to think about using them with respect to 2 loudspeakers and headphones as well. And then we want real instruments in here so they can have that experience. And so now we can start to, and then we'll have the auditory model telling us something about what the estimates are of the dissonance. Now, a couple of observations. We want to get, I'm going to skip, just so we can get the workload that we have to get done, I'd have to go into more into this Bregman-Wright hypothesis, and I want to do that a little more. I got to go back and read those papers, that whole chapter 6, or chapter 5 of the Bregman book goes into this. And so does David Huron and so on. But you can see it's going to make a difference. Once we have them really separated, we just don't get the beats. And then once they're partially separated, we're going to see that maybe the auditory system can in fact tease them apart and not have as strong of effect of the dissonance. Okay. Now, God, there's another thing. Let's move on to now really rich, complex, cluster-like chords and so on. In fact, before we do that, maybe we should look at some standard chords. Minor triads, major triads, 7th chords. We're going to do some little chord composing thing. Maybe, how about dyads to 4-note chords in the interface. So you can do a little orchestration with real harmony, and then you can select from a vocabulary of harmony here and play with the spectrum. It's just an elaboration of this particular type of thing up to a higher level. And of course this diagram wouldn't be in that interface because it's going to be more complicated to just have the 4. Now I want to move into what happens when we get into the massive stuff, which is that is the migrator style stuff and so on. Okay, now I need to explain an underlying sort of idea about how it is that the brain, how it is that we come to have the sensation, a sort of single percept of roughness for complex tones with many auditory filters. And I need to expose here in this place, and again, I'm skipping through a number of topics right now. So I need to expose the idea of an additive combination of roughnesses. So you get a roughness out of a frequency band in the high register, a roughness out of these bands, and so on. And now what we're going to do is sum those roughnesses across those. And these are going to be, subjective, magnitudes from subjective experiences that we're going to add together to produce an overall magnitude. And we might ask the question, well, is that sensible? Does the brain have a kind of additive mechanism of some sort? And I don't know that I need to go into this in great detail about the experiments that I ran. So, I think that we can let the real gnarly details of what additivity means on the side for a moment. But that additive model does work pretty well. And so what that additive model looks like is something like the overall roughness from a subjective point of view is somehow the sum of the roughnesses in the various frequency bands in each of the, if that notation makes sense. So I've got a measure of roughness here, subjective measure, and then I'm going to somehow add all those together to give an overall measure. And that turns out not to be a bad model. It's a very good first approximation. Now you can understand that when things get close together, I mean, when adjacent bands are probably going to, since they overlap heavily, there's going to be some interaction terms there and so on. So the more complex picture would be shown in the auditory model, because the filters there, these gamma tone filters, are actually overlapping. Okay, so examples including things, and now we want to maybe take some examples from the real musical literature somewhere. Some chords, some different, maybe things taken from different orchestral things. I mean, we could have some stuff from Xenakis, some really dance cluster-like things, or we can have some Messiaen harmonies and so on that could put together there. Okay, now the additive model, maybe we have to be a little careful here. Now, here's the thing. If the undulations in amplitude in the separate bands are non-correlated with each other, things aren't going to be nearly as rough as if they're correlated. So I got to nuance this. I got to be careful here. I don't want to throw this out there. It's going to confuse people. I say it's additive for one moment, then I go back and say, hey, wait a minute, it's additive if and only if they're really moving together, or they're, because when they're not correlated, and this is some work from Daniel Presetzer, who's done these experiments to show that when they're synchronized with each other, they tend to get even more rough. Shoot. I'm just thinking how hard it is to explain all this stuff. All right, now, somewhere along the line, I've got to go in and say, well, now what we're going to do is try to really look in more detail about what's going on in the auditory nerve. And then I want to introduce these diagrams here from the gamma tone filter bank, or what would actually be a simulation of what's sort of being passed on up the auditory nerve. In other words, these kinds of plots here, and have to describe how each of these lines is in fact a separate filter bank output. And then you'll be able to see synchrony in the way things are either undulating in synchrony with each other or desynchronized and so on, and that's gonna play a role. So that we need to refine a little bit, and we can get. I think once we learn a little bit more about this ear model and the way we're going to put it in here, we can do that. Okay. Now there's got to be a little bit of a historical section here where we talk about a sidebar maybe, or thinking about when these ideas started to. So I think it'd be worth saying a little bit about the way in which Pythagoras found, these small integer frequency ratios important, and there was kind of this, this sort of very numerically almost, notion of consonance and dissonance. It had more to do with the frequency ratios. They'd take the monochord and divide it up and so on. So there's that, and then we got to talk about why that is the case here, because when the frequency ratios are consistent with each other, we need to show a way of how these things really lined up, and we don't get the beating in the same way. If it's 3-2, there's some components out there, but they aren't interacting with each other to quite the same extent. There are some that are going to interact because they're left dangling out there, but when we have a unison or an octave, you get this really complete match and smooth spectrum. So we need to trace that maybe up through Helmholtz's. I mean, there's not much to say between Pythagoras and Helmholtz that I'm aware of. I just was reading in this book. This is a musicologist who is writing about a sort of perceptual view of music theory, and he goes into this Pythagorean view of the world. I was getting into this the other day. Anyway, we might, some of that history might get in there and how it can. Anyway, it's. I'm sorry, I'm rambling on, but what I'm doing is free associating right now, stuff that we got to get sort of woven in here, some kind of historical thing. And then after Helmholtz, the next big thing that happens is in the 60s, when the Dutch psychoacousticians start to understand the notion of auditory filters, and when they do these experiments with beats and so on, and so this is Plomp and Levelt, and then this goes on into Terhart and so on. So it's kind of interesting. It's Pythagoras, Helmholtz. Those are the key points from my view, and then we get into the sort of psychoacoustic view of this, which actually doesn't really take place until the 60s or so. How to explain this? So, and then of course now and then the next big step is to say, hey, we need auditory models to understand this in a better way. And I don't want to diss all these people like Sarth and Sarth, but we got to say that we got to point out that some of the results from some of the calculations that people have made about consonant dissonance are off the mark, because they don't take into account the physics of the situation. We have lots of tones interacting with each other, so I need to explain something about that, so that you end up with a smoother thing. Then I think it'd be worthwhile at some point saying something about how the environment in which the music is played is also going to influence the sense of roughness. Because when you're in a real room, and you've got reverberation, and you've got you end up smoothing out things. In fact, I remember a really striking demonstration by Juan Roeder. He's an organist as well. He used to organize these conferences in Osijek, in Austria, where he could go and play these organs in these churches. So at one conference, we were there, and we go up in the organ loft, and we're writing these pipes, and he's playing these intervals, really rough sounding, and then he does the same thing. We go to the back of the hall, and things are remarkably different sounding because of the reverb. So that needs to be brought up here too, because it isn't a realistic view otherwise. So what we're introducing here are things like the binaural, the spatial layout being important, and also now we introduce the role that room information plays. And then I've got to, and somewhere in the process here, get the ideas across that this can't be the whole story. Because that's a nice segue in. I mean, the room, so it makes everything smooth, then what's the deal? Does somehow the musical character change? Does stuff that would otherwise, I mean, it's going to sound smoother, but the functional harmony doesn't change. So we need to say some things like that that demonstrate that this isn't the whole deal. So why isn't it the whole deal? Well, there's other ways of reasoning about tension, release, and stability, and so on. And there I'd like to introduce what would be one of the previous units in this will be about how we perceive pitch, and how pitch is calculated, and how we don't necessarily need to have fundamental frequency. That'll be one lesson too. It'll be about the virtual pitch concept and lots of examples. And then that'll relate to the harmony where you're looking at roots of chords. We'll tie that together. So maybe we'll have some notion of stability or dissonance, constants of dissonance related to whether the pitch, the virtual fundamental is, you know, is clear or whether it's unclear. Well, I mean, it's unclear for complex harmonies, but actually, you know, I don't know if I dare do this around musicians. Turns out the Tristan chord actually has a virtual pitch of C sharp down at the bottom. And when Terhart presented this, these music theorists went berserk. They said, "No, what are you talking about? That's not a." And then later on, this inspired us to kind of take a look at that. And it turns out that Wagner actually goes through a fair amount of trouble to keep it from sounding that way. But anyway, there is that rock bottom. And then more recently, I've seen analyses of people who've incorporated this idea into their work. So we might want to do something with that. Don't know. Now I think got to spend some time explaining the graphical output from these ear models and how it's going to how to interpret it and so on. So we need to. By the way, this will give you virtual pitches. This particular thing is a virtual pitch analyzer too. It does give you what Patterson calls a ribbon model of pitch and so on. It's one of the better. And in fact, that ear model demonstrates most of the phenomena from laboratory experiments in pitch perception, pitch shifts, and so on.